All right, CMOS inverter, we all know, is one of the fundamental building blocks of CMOS digital circuits. CMOS digital circuits, which is the dominant semiconductor technology of present-day electronics. And therefore, it's important that we understand the CMOS inverter as well as we can. And one of the things about CMOS inverter is the size of the inverter, which is not dealt with in many textbooks in as much detail as perhaps it deserves. So let me illustrate what we mean by the size of the inverter, and let's briefly discuss what the impact of size is. So we've shown here a CMOS inverter here, and so let's put in some size information. So let's call this the size of the Nmos. So let's say this is W by L, and let's use the minimum size here, right? So what we are going to just build is an inverter that I would like to call it as 1x inverter, and where we are using the size of the Nmos, the width of the Nmos, and the length of the Nmos, which are minimum possible that are allowed by a given technology. If it's, let's say, a 0.5 micron technology, then L, minimum L that we can choose is 0.5, and W may also be similar. So that's the minimum dimensions, the width and the length of the Nmos here. And the Pmos would be a factor higher, let's say alpha times W by L of the Nmos transistor here. And alpha, we would like to make the inverter balanced. The driving strength of Pmos should be similar as the driving strength of the Nmos. And because the mobility of holes is smaller than the mobility of electrons, so the size of the Pmos is made 2 or 2.5 times higher here. So that's this factor alpha. We'll not get into the details. The factor alpha is here. So when we use the minimum width and minimum length of the Nmos, and we make the Pmos sufficiently larger than the Nmos, let's call this inverter as the size 1x. This is like the minimum size of the inverter that we can make. Alright, so we'll call this inverter 1x. Now suppose I make the size here 2 W by L min, and proportionately increase the size here 2 alpha W by L min here. So this is the width. Basically the width of the Nmos has been made twice as large as the width of the Nmos over here, and similarly the width of the Pmos has been made larger. So we call this inverter 2x. Is drive strength, because the width, the current that Nmos and Pmos can carry is proportional to the width of the MOSFET. So its drive strength is twice as large as the first one here. And similarly, if we want to make it a inverter which is 4x, then what we do is we make this 4 W by L minimum, and proportionately we'll make it 4 alpha W by L minimum here. So that would be an inverter of drive strength which is 4 times the minimum size inverter here, right? So 4x, and similarly we could make 8x and higher also. So the issue is, why are we doing it? Why are we not happy with the 1x inverter here? Why do we want to make it 2x and 4x here? So before we get into that, it's important to look into an issue which is actually dealt with in a fair bit of detail in many of the books, which is the relative size of the Nmos and the Pmos, right? So we've said this is W by L here, and this we make alpha times W by L here. And so the relative sizes are basically to achieve a particular voltage transfer characteristics. And often we want a symmetrical voltage transfer characteristics. And remember, from voltage transfer characteristics we get noise margin high and noise margin low. And sometimes we call, often we calculate this quantity called inverter threshold voltage here. So we call this V inverter here. So all these parameters, inverter threshold voltage, noise margin high, noise margin low, they all depend actually on the ratio of the Pmos and the Nmos. They don't depend on the absolute size of the NMOS or the absolute size of the PMOS, but on the ratio. And as an example, when we calculate V inverter, V inverter is at this particular point where both the PMOS and the NMOSs are in saturation region. And obviously the current through both the NMOS and the PMOS, they are connected in series, is the same. So when we use an equation for NMOS in saturation, when we use an equation for PMOS in saturation, and we use the fact that source to gate voltage of PMOS is VDD minus V inverter here, so we are applying V inverter here, and this is V inverter here, right? So this line here is V out equal to V in line here, right? That's the line here. So at this intersection point, the voltage at both ends is V inverter here. All right, so we define this here, VDD minus V inverter here, and these are the standard definitions of W by L times KPN, WP by LP KPP here, and we can derive this expression here, right, V inverter. And the important point to note here is that the V inverter, which defines basically how symmetrical or asymmetrical the characteristics VTC is, it depends on beta R here. And beta R, note that beta R depends on the ratio of the sizes of NMOS and PMOS. It doesn't depend on the absolute value, just the ratio. So similarly, noise margin, NMH and NML they depend on the ratios of the sizes rather than the absolute values here. And we said that if you want to keep the characteristics symmetrical, then this ratio we have to because KPN and KPP are different, so we keep the ratio KPN and KPP maybe this ratio may be, let's say, 2.5. So we make the size of the this thing here as 2.5 here, right? To make the beta R basically equal to 1. And if the threshold voltages are similar, so that sort of places the characteristics or inverter threshold voltage right in the middle, and we get a symmetrical characteristic. So the point that one is trying to make is that if we look at voltage transfer characteristics, we look at NMH, NML, inverter threshold voltage, these are affected by the ratio of the size of NMOS and PMOS, not by the absolute values here, and that is signified by the beta R here, which depends on the ratios here. So what depends on the absolute size, right? So we said 1x and 2x and 4x. So what depends on the absolute size is the delay. So let's look into the delay here, propagation delay, right? Propagation delay here. So what depends, and so to understand delay, one has to keep in mind that delay comes about because of capacitances. So we have an inverter here, and basically because there's a net capacitance at this output node here. So if this is V in, this is V out, there is a net capacitor here at this particular node. And as the inverter, as you apply 0 to 1, then the output will go from 1 to 0 here. Is basically the delay comes about because the capacitor at this particular node has to charge and discharge. So what are those capacitors? Well, there is a capacitor here due to the NMOS between the drain and the gate. There is a capacitor here between the gate and the drain of the PMOS. Then we have not shown there is a body terminal here which is also connected here, and there's a body terminal here which is also connected. So there's a capacitance between drain and body, and there is a capacitance here between between drain and body here. So there are all these capacitors that have to be charged and discharged, and the delay comes about because of the time it takes to charge and discharge the capacitances. And for example, if you have to charge the capacitance, it has to charge through PMOS. If you have to discharge the capacitance, then it is discharged through NMOS. And both PMOS and NMOS, they have resistances. And so it's practically a RC delay. It's like an RC delay that we are well familiar with. And so let me remove these capacitors there. So, when we apply a, let's say 0 to 1, if we apply an abrupt signal here, say we go from 0 to VDD here, then the output will go from VDD to something like this here, right? Gradually it will go VDD to 0, and there is a propagation delay. And if we consider this particular inverter, This propagation delay, we will call this as the, let's say, tau p intrinsic. It is intrinsic delay here, TP or tau p intrinsic delay here. We call it intrinsic delay because there's nothing connected to the inverter right now here. So there's an intrinsic delay. And the intrinsic delay, as we said, depends on the intrinsic capacitances of the inverter and depends on the drive strength of the Pmos and the Nmos here. So there's an intrinsic delay here. And let's, for the sake of discussion, suppose that the intrinsic delay for our inverter of size 1x is 20 picosecond. Now what happens is, if you make an inverter which is 2x here, right? If you make an inverter of 2x, so what happens is, when you make the size of the Pmos, Nmos double and the size of the Pmos double, what happens is that the capacitors also tend to become higher. You know, first order approximation, the capacitors also tend to become double. First order approximation is not exactly that. And then the current available for charging, we know that the current is proportional to W, right? So so the current available for charging the capacitor also doubles. So as a first order approximation, when you take a 1x inverter and you say its intrinsic delay is 20 picosecond, and you make a 2x inverter, which is twice of W by L minimum here, its intrinsic delay is also 20 picosecond, first order. Okay, it may change a little bit, but let's keep intrinsic delays 20 picosecond here, right? So as you increase the size of the inverter, as you go from 1x to 2x to 4x, the intrinsic delay, the delay of the inverter itself, remains practically the same here. Now this particular diagram here basically shows you those capacitors that we were talking about. This is the body here, and there is a drain to body capacitance here. This is the capacitance that we talked about. Similarly, this is the drain here. So there's a drain to body capacitance here that we were talking about. And of course, there's a drain to gate capacitance and drain to gate capacitances and all that we just talked about. So this schematic shows you where the capacitances are. And these capacitors are an essential part of the MOSFET, so they're always there. And during switching, they have to be charged and discharged, right? So that's the intrinsic delay of the inverter here. And for the sake of discussion, we'll take it as 20 picosecond here. So let's come back to our, let's consider this a case of, let's say this is a 1x inverter here, and both of them are 1x inverter here for the moment here, right? So now let's focus our attention on this. Now, right now, there's nothing connected to our inverter 1, and this is inverter 2. There's nothing connected to inverter 1, and that's why its delay will be the intrinsic delay, which is 20 picosecond. But now let's connect this up here, right? So it becomes basically this particular circuit here, right? And we are focusing on this one here. What will be the delay of this? So now the delay will become, total delay TP will become TP intrinsic plus TP, let's say extrinsic here. Extrinsic means something that is not the original part of it, but because of the load. So this inverter acts as a load, and this inverter acts as a load, and load in the sense that it adds a capacitance to this particular node here, at this particular node here. Note that there's a capacitance now between here and here, gate to drain. There's a capacitance between gate to source, and similarly there's a capacitance here and there's a capacitance here. So there is a load capacitance, and therefore that additional capacitance, so there's an additional capacitance here. Now, if we you know, we could model it by saying that the effect of the next inverter is to add another capacitor here, which is the load capacitance. So this load capacitance also has to be charged and discharged, and that's the reason for this extrinsic delay here. And this extrinsic delay, we often model it as a factor, let's say K times the load capacitance here, CL, right? So K, as you can see here, has units of resistance. So that depends on the driving strength of this particular inverter here. Because note that if the capacitor has to be charged, it has to be charged like this here. If it has to be discharged, it has to be discharged like this here. So obviously it depends on the driving current of the Pmos and the driving current of the Nmos here. So So when we have a 1x inverter, let's give some numbers here. We said this is 20 picosecond, right? This is 20 picosecond. Now this one, let's take a number here, K driving strength. So we can write it as 4 picosecond as a number divided by 4 femtofarad here. Okay, so note that it has units of resistance. You can verify that capacitance by time by capacitance will give you that here. So K times CL here, and CL is what? CL is the input capacitance of the inverter here, right? So let's come back here. Let's look at this one here. So both are 1x here. So we are saying the total delay TP will be TP. Let's write it intrinsic plus TP extrinsic. Intrinsic we said is going to be 20 picosecond. Extrinsic we said will depend on K times CL here. And K we said was 4 picosecond by 4 femtofarad. So what we have to know is, to calculate the total delay, we have to know what is the load capacitor here. Capacitance looking from here, because that's the load for this particular inverter here, right? We are calculating delay of this particular inverter here. So let's take CL as 4 femtofarad here. The load of 1x inverter is 4 femtofarad here. So our total delay then becomes TP will become 20 picosecond plus 4 into 4. So it will become the 16 and it will become 36 picosecond here. Right? So when you have an inverter just by itself, its delay will be 20 picosecond. But when you connect another inverter to it, well, its delay, this inverter here, its delay will become 36 picosecond because of the additional load that is there here. Right? So there are two components of delay. Intrinsic delay, which is independent of the size, extrinsic delay, which depends on what is connected, what is there as a load here. Right, so now there are two things about the extrinsic delay that we need to understand here. So the extrinsic delay we just saw is K times CL. And K is the driving strength of the inverter here. So for example, we just took a value of K equal to, K of 1x. Let's say K of 1x inverter is 4 picosecond by 4 femtofarad. Now if I were to make this inverter 2x, twice the size. So now what would happen is, if it were 2x, the size of the Pmos is doubled, the size of the Nmos is doubled, the amount of current available for charging becomes double, and the amount of current available for discharging becomes double. So K 2x will be half of this, half of, 4 picosecond by femtofarad here. This is not 4, this is 4 picosecond by femtofarad here, okay? And so K is 4, this thing here, so it will become half of 4. Units are we writing it as femtofarad, so it will become 2 picosecond by femtofarad here. On the other hand, if you make the size 4x, then the sizes become 4 times, and therefore K will become 1/4 of whatever was K of 1x. So it will become 1 here. Right, so that's how K gets scaled here. Right, so you can obviously see as K gets scaled, then the extrinsic delay will become different here. All right, so let's take an example here. Suppose it's like this here. So this is 1x and this is 1x. Right, so and we are focusing on the first inverter. What will be the delay of the first inverter? TP will be intrinsic delay, 20 picosecond. Extrinsic delay will depend on K, 4, times the load capacitance, which is also 4. So we just said it will become 36. All right, fine. Let's do the following here. Let's do 2x. Suppose this is a 2x inverter and the load is 1x. So next TP will be equal to the intrinsic delay of this 2x, which is same as 20 picosecond. Intrinsic delay doesn't change. Next is K times CL, right, the extrinsic delay. K will become half because it is 2x here, right? So it will become 20 picosecond, 20, plus half of the 4 value here. So it will become 2, and the load capacitance is still the same because it's 1x. So it will become 2 into 4, and so it will become 28 picosecond. So note that the delay decreased. Delay earlier was 36 picosecond, now the delay is 28 picosecond. And which part of the delay decrease is the extrinsic delay here. And why did the delay reduce? Because we made the inverter 2x, so its driving strength became twice as large, and therefore it could charge the capacitance, the load capacitance, twice as fast. Okay? Again, suppose we make it 4x. And this is still 1x. Well, what will its delay be? Intrinsic delay will remain the same, 20. Now k will become 1/4 of original value, which was 4. And the load capacitance is still 4. So this will become 24 picosecond. Right? So if you make the drive strength 4x, and if you make it 8x and even higher, you would note that it will tend towards the only delay that will be left is the intrinsic delay here. So that's how, for example, the size of the inverter plays a role in terms of the delay here. You can make the inverter, we have seen that as you go from 1x, the delay was 36 picosecond. With 1x, 36 picosecond. With 2x here, 28 picosecond. With 4x here, 24 picosecond here. Right? There's another side here. What happens like this here? Suppose we take 1x inverter here, and suppose it is driving a 2x inverter here. Right? So again, how will we do delay? There will be intrinsic delay, 20 picosecond. Then k for this one, which is 4, and the load capacitance of this one. So load capacitance of this one will be twice, because its size has become double, so will be twice of the earlier value, which was 4. So this will become 8. So 4 into 8 is 32. Right? So it will become 20 and 32, so 52 picosecond. Right? So it will become 52 picosecond because the load capacitance is higher here. Right? So we are seeing, for example, what the size of the inverter, the way it has an impact on the delay here. Now, consider again the following case here. So let's use a page here. All right. So suppose we have an inverter like this here, and suppose this inverter has a fan out like this here. This, and fan out of 4. Right? We are again focusing on this particular inverter, and let's say all of them are 1x here. 1x, 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 1x here. And we are asking what is the delay of this particular inverter. So that will be equal to intrinsic delay, which we are taking as 20 picosecond, plus the k value, which is 4, plus the load capacitance. Now each inverter will add a load capacitance of 4. 1x inverter is a load capacitance of 4. So we have 4 into 4. So we have 4 into 4, and therefore you can see what the value will be, 20 and 64. Right? 16, 64, and that will become 84 picosecond. Now, this 84 picosecond delay of this particular inverter may be very high. It's becoming very high, and so you want to do something. So one of the things that you could do is that inverter, I could, instead of 1x inverter, suppose I make it 4x inverter here. This one, I make it 4x. And the load remains the same. Right? 1x here, 1x here, 1x here, 1x here. So what will be the delay now? So TP will become we are focusing on this inverter, delay of this inverter. So intrinsic delay again 20. Now its driving capability is 4 times higher. So the K factor will be 4 by 4. It will reduce by 4 by 4, and the load capacitance is still the same, 4 into 4. So this will become 20 plus 16 and 36 picosecond. So look at the difference between the two. If everywhere we use 1x inverter, we would have gotten 84 picosecond here. But now because that inverter, which has a higher load, we increase its size to 4x. Well, the delay of the fast inverter becomes 36 picosecond. So that's where we use inverters and we use gates of different sizes depending on what the load is and how much delay we are looking for here. And note that delay reduction is not as simple. We have seen that when we make this inverter 4x, we have reduced the delay of to 36 picosecond. But what we have done is that the capacitance looking from here has also become 4 times CL here. So some other gate may be driving it. So its load is increased. And therefore the delay of that particular gate is increased here. So we have to do this kind of a balancing act and see where it makes sense to increase the size of the inverter in the gate and where maybe it is not as beneficial. All right, so with that we have seen that just like the inverter, we make sizes as 1x and 2x and 4x and so on and so forth. There are other gates also. We may make a AND gate which is 1x, and we make a AND gate another which is 2x here. So basically what we are doing is we are changing the driving strength of these particular gates here. And in all of these cases, as a simple model, we can think of propagation delay as made up of an intrinsic part plus an extrinsic part. And intrinsic part, first order of approximation, remains unchanged. The extrinsic part is made up of a factor called K times CL. And the K represents the drive strength. And if you have, so K of 2x will be half of K of 1x. K of nx will be 1 over n K of 1x here. So that's the benefit that you get by making the inverter of higher sizes here. The K value, the driving strength value, that reduces, and therefore the extrinsic delay reduces here. All right, so before we leave this particular topic, I just want to add one more thing about the area of the inverter. So far what I've been saying is that we have inverters of size 1x and 2x and so on and so forth. What really happens to the physical area? So when we talk about physical area here, physical area as you go here. So I've shown here one data that is there here. So this is the inverter of size 1x. And this is the actual physical area. So this is the height of the inverter, and this is the width of the inverter. So total area is 6.5 units. Now for the sake of comparison, let's look at an inverter of strength 4 times higher. And the height is here 5 and the width is here 2.6, and so the area is 13. So when you go from 1x inverter to 4x inverter, the difference in actual physical area is only 2. So don't think that when you make the width of the transistor 4 times as large, width of the Nmos transistor 4 times as large, and width of the Pmos as 4 times as large, the overall area of the inverter will also become 4 times as large. That's not true. The overall inverter area is only becoming a factor of 2 higher here. And if you would like to understand why this happens, then you have to go and look at the layout of the inverter, the physical layout of the inverter. So which is shown over here. Physical layout of the inverter here is shown over here. So I'll not go into the details. On the channel you'll find more discussion related to layout. But basically this is where the Pmos is. This is where the Pmos is, physical Pmos, and this is where the Nmos is. So the first thing that you note here is that the overall inverter is considerably larger than just the the transistor part that you see here. And so when you are doubling the size of the Pmos, what you're really doing is this portion that you see here. This portion is the there you're doubling the size of this one. Similarly, when you're doubling the size of the Nmos, this is what you're, this is the portion where you're doubling it here, right? And the inverter, overall inverter that you're seeing is larger than that. There are metal interconnects, there is a body contact, all of that is there here. And they do not scale linearly with, they may not change or they may not scale linearly with simply the width of the Pmos or the width of the Nmos. So the area simply does not scale. If you simply double the width of the Pmos and the Nmos, the overall area of the inverter does not become double. And the idea was that this particular example was illustrating that here. that how does the physical area of the inverter, because remember that as we are trying to reduce the delay by increasing the size of the PMOS and the Nmos, so obviously the area of the inverter also increases. And the area of the circuit is always a concern for in digital in circuit design. The larger the chip area, the more expensive in general the IC will get here. All right, so let's stop here.